In this lecture, we're going to be talking about measurements and units. The first question that should come up in your mind is, what is a measurement? Measurement is a quantification of any variable. For example, if you didn't know how to measure things, you wouldn't be able to tell how much a bag of potatoes weigh. And if you're like me, that would be a disaster because you would like your maximum share of potatoes. So once you know how much a bag of potatoes weigh, you couldn't make sense of that measurement if you didn't have units to accompany that measurement. For example, say your bag of potatoes weigh 8 pounds or 10 pounds or whatever. What is that pounds label at the end of the measurement? 8, 9, 10, whatever. That pounds, LBS, is a unit that makes sense of that measurement. So as we can see, measurements and units go hand in hand together. So units actually make sense of any measurement. And in physics, making sense of things is really the point, right? So there are various systems of units. For example, in the USA, you use a different system, which measures weight in pounds, height in feet, speed in miles per hour. But in other parts of the world, you may have weight being measured in stones or speed being measured in kilometers an hour, and so on and so forth. But in physics, to keep things uniform everywhere in the world, we use a systematic representation of units. We call it the SI system. So in this course and in most basic physics courses in general, we'll be sticking to SI system of units. So what does that system represent? So we have the basic quantities or basic variables, length, time, and mass, being measured in meters, seconds, and kilograms, respectively. So meters can be denoted by M, seconds is denoted by S, kilograms is denoted by kg. From these basic units, from these basic quantities, all other quantities can be derived. So the derived quantities, for example, speed has a unit of meters per second. That signifies that we have meters over second, meaning speed is a quantity defined in terms of length divided by time. As we have mentioned that there are a various number of systems of units. So it is important that we are able to go back and forth between different systems of units. For example, you should be able to, or you're expected to be able to solve problems which involves taking care of the fact that you maybe need to convert a measurement given in miles per hour to meters per second to solve the problem in physics, right? Because we want to maintain that SI system of units. So conversion between units is between different systems of units is important. Also, conversion between different bigger and smaller measures or bigger or smaller unit is important as well. For example, if you want to go from a smaller unit to a larger unit, then you would want to have the amount in smaller units over a conversion factor, that is, whatever amount of smaller unit are given, divide that by the conversion factor and multiply that by one larger unit. For example, if we have meters and which is a smaller unit, and we want to say convert that to kilometers, which is a larger unit, then we would take the amount in meters. For example, let's say we have a measurement of 10 meters in the numerator, and then divide that by the conversion factor to go from meters to kilometers, which is 1 kilometer is equal to 1,000 meters. So we divide 10 meters by 1,000 meters and we multiply by 1 kilometer. What happens is the meters go away and we end up with a unit in kilometers. So 10 meters is equal to 0.01 kilometers. Okay, we can do the other way as well. We can go from larger units to smaller units, which would involve taking the amount given in smaller units and multiplying that by a conversion factor and dividing that whole thing by one smaller unit. For example, if you have a measurement given in seconds and you want to go to milliseconds, what you would want to do is say we have a measurement of 10 seconds. We want to take that 10 seconds, which is a larger unit than milliseconds, and multiply that with the conversion factor, which in this case is, again, 1 second is 1000 milliseconds, and we multiply that and we divide that by 1 second. So what happens is the seconds go away and we end up with 10 seconds is equal to 10,000 milliseconds. Now let's introduce ourselves to the dirty business of physics, the really dirty business. What are those? Equations. But there's nothing to be afraid of. Equations is what makes sense of everyday life, starting from the very minute objects like particles that make up the universe to the biggest objects like planets that we live in, like Earth, like everything that is revolving around the sun in an orbit in the solar system is described by equations. So equations, if they weren't there, well, probably we wouldn't be here, right? So what is an equation? So equations are mathematical expressions that have very specific purposes, and to my mind, they must satisfy two criterion. So one of the criterion is pretty basic. This is the expression must be separated or related by the equal sign. And so this is pretty basic. So equation comes from the presence of this equal sign. So if we say that one side, we have two sides to an equation, which is a left hand side, which is left of the equal sign, and a right hand side, which is right of the equation sign. So if we didn't have that equal sign, we wouldn't have an equation, right? So what does this equal sign do? It relates the two sides of the mathematical expression, and equal means that the two sides must be consistent with one another. So if you're doing a mathematical operation on one side of the equation, say you're adding a number, you would have to add the same number to the other side of the equation, otherwise the equation won't work. Another criterion that is, to my mind, vital to equations is, and especially in physics, is they must have same units on either side of equals. Okay, so both left hand side and right hand side of the equation must have the same units in physics, right? Otherwise they're not describing consistent quantities, so there must be a faulty equation, right? So let's look at an example. Let's use a different color here. Okay, so let's say we have an equation x equals w over y plus z. Okay, and now we are told some things about the equation. We are told that z has units of kilograms per meter squared. So we denote that by square brackets of z. Square brackets basically means dimension of this quantity dimension of this quantity means units of this quantity. So this quantity has units of such and such. So this Z has dimensions of kilograms per meter squared. So, and also remember, these are probably fictional quantities, and we don't need to know what Z's and what W's and Y's are. We just want to consistently check this equation, right? So let's say we have Z measured by kilograms per meter squared, and W is measured in meters. So we could say W is a sort of length, whatever that length may be. And we are asked, what is the dimension of Y? Okay. So initially I would think, okay, this is weird. I've never done such a thing. And how do I determine a dimension of a variable in an equation by just knowing the dimensions of other variables, some other variables in that same equation? Well, we just look at the second criterion and see that for an equation to be consistent, they must have the same dimensions or same units on either side of the equation. Okay, so the overall units of x must be the same as the overall unit of this whole operation. So W over Y plus Z must each have the same unit as x. Okay, let's see. So first of all, Z, as I mentioned, must have the units of x. W over Y must have the units of x. So we know that Z is measured in kilograms per meter squared. That means x must also be measured in kilograms per meter squared. Okay? So we can write down dimension of Z. This is my solution. So dimensions of Z is the same as the dimensions of x is the same as the dimensions of W over Y, right? Okay, so we know that Z and x must both be measured in kilograms per meter squared. So we write kilograms per meter squared on this side and investigate the dimensions of each variable on this side, on the right hand side. So dimensions of W over dimensions of Y. So we know the dimension of W given to us as meters, but we don't know, and we want to find what is the dimensions of Y. Okay, so let's go up here. So we have an equation which is looking like kilograms per meter squared equals meters over dimensions of Y. And remember our target, that's our target. Okay, so what is the next step? Next step, the easiest way we can do this is cross multiply. So what does that mean? Cross multiply equations mean denominator of one side is multiplied with the numerator of one side, and vice versa. Denominator of another side is multiplied by numerator of the other side. Okay, so Y is multiplied with kilograms and meters is multiplied with meters squared. So we end up with this expression, or this equation to be more exact, and we divide. We want to separate out, or we want to solve for dimensions of Y. So we divide both sides by kilograms. So if we do that, kilograms go away. That gives us the dimensions of Y is meter cubed over kilogram. Now you might say, hold on a minute, but this guy just said that each of these terms in the equations must have the same units as z and x, meaning each of these terms must have a unit of kilograms per meter squared. Well, yeah, y is a part of one full term. The overall units of the term, w over y, the overall dimension, has to be kilograms per meter squared. Is it so? Let's check. Let me erase this. So w over y has dimensions of kilograms per meter squared, and we want to check that. What is the unit of w? So we want to investigate the left hand side of this equation right here. So left hand side of this equation is w over y. So we can separate out the dimensions of w and y to make the check. So what is dimensions of w? Is meters. What is the dimension of y? We just calculated this to be, so we just divide w over y. So y is meters cubed per kilograms, okay? And this means, dividing just means we flip and multiply. So we flip meters cubed over kilograms to kilograms over meter cubed and multiply with meters. Voila, we end up with this whole term w over y having the dimension of kilograms over meters squared, which is what we said must be true for the equation to be consistent, and it is. So the important thing to realize is that overall term w over y must have the same dimensions as x and z.